It's a pleasure to be here in Sofia and give this talk. So, as Martin said, my name is Dragomir. I lead the natural language processing group at Yale University, and the name of the group is called actually LILI. I'll tell you later why. It stands for Language, Information, and Learning at Yale, and we deal with all issues related to information retrieval, natural language processing, computational linguistics, and some types of machine learning. So this is our nice campus. I hope you all get to visit one day. So NLP applications are common everywhere. You all have some of those running on your phones. You use search engines all the time. You use machine translation. You use speech recognition systems, use auto-completion, email assistants, and so on. So just like yesterday, Christina's first talk during this conference was about some of the issues in NLP. Today I'm going to talk about something slightly different, in particular how to build personal digital assistants that can understand natural language and use that to interface with structured data in the form of databases and knowledge graphs. So, as you can probably imagine, people have built many different natural language interfaces over the years. Some of them have to deal with image retrieval, video retrieval, and others are more about web pages, tables, knowledge graphs, and databases, and so on. Now, on this end of the spectrum here, we have open data or unstructured data, essentially in plain text, whether it's in English or in Bulgarian, or in Korean, or some other language. Then the other extreme is much more structured data, typically in the form of relational databases with joins and multiple complicated schemas. So this is the area where I do my work these days on semantic parsing for structured data. So let me give you an example here of an interface between a user and a natural language system. So we have databases and tables in structured format, and then the user wants to ask some questions. For example, how many hoverboards are left in stock, or which department has instructors that have high ratings. Then this gets sent to the database, and then we have some accessible data insights, for example, the most salient information that you can extract from the table, answers to the questions, and so on, and then generate those in text or in some other multimedia format back to the user. So our goal over the last few years has been to close this loop. So we have worked both on semantic parsing, essentially the text-to-data part of the project, and then also on generation, which is the data-to-text aspect. So here's an example of SQL. So SQL is the structured query language. Some people call it also SQL. Those are different queries for relational databases that help you answer the questions on the previous slide. Now, if everybody were an expert in SQL, they would just go and ask those questions, and that's what database administrators and database managers do. However, we prefer that people can use their natural language abilities to query database. In this case, they don't have to understand SQL, and they don't need to understand the actual structure or the schema of the databases. So in this case, they would just ask things like, how many hoverboards are left in stock, or give me the arriving time of Czech Airlines 327, and so on. So I'm going to talk about 3 recent papers that form the different parts of this loop. So the first part is about understanding the user. So understanding the user involves semantic parsing, converting the natural language utterances that the user speak into some meaning representation or semantic representation. And this can be done in multiple ways. We're particularly focusing on SQL generation, but also more recently on executable code generation, where you can actually produce Python or some other programming language as the output. Then you have the understanding the data part. So it turns out that in order to build efficient text-to-data, data-to-text systems, you have to be able to understand the structure of the data and to pre-train a model that is specifically tuned to tables that have columns and records and also joins and other complicated schema things. And then we also need to be able to generate an output to the user. So this is something that we call structured data-to-text generation, but it can also be in the form of question answering. For example, how many hoverboards are left, or also summarization. For example, what are the most important highlights in this particular database? Okay, so let me show you an animation of how this thing works. So you have a user, you have a database. The database is generally complicated. It has multiple joins and foreign keys and aggregate queries and so on. And then we want the user to be able to ask a question. For example, which European countries have some players who won the Australian Open, Tennis Open in at least 3 times? Okay, then the semantic parser, in order to be able to answer this question, has to be able to convert this question into a SQL query. And as you can see, the SQL query is actually pretty complicated. It has a join between multiple tables. You have a join condition here. You have a select statement. Then you have grouping by a certain attribute. And then you have an aggregate query here, essentially saying how many of those groups have counts that are greater than or equal to 3. So this is something that then gets executed on the table, and then you get the answer, for example, based on the different components of the query. So if you want to train an end-to-end system, you have to be able to have at least the following things. Either you have an input in the form of natural language and an output in the form of a programming language. So this is what we call the fully supervised setting. Or you can also have something called the semi-supervised learning setting, in which case this is hidden. It's a latent variable that you have to infer from the data, and the only thing that you're given is the question, and then the answer to the question. So you know that you can arrive to the answer based on the question by first converting to the executable code, then executing the code, but the executable code is actually not available to you. So we have done a lot of work on both of those scenarios, both with fully supervised and weakly supervised learning. Okay, let's see some of the challenges that appear in table semantic parsing. So I'm going to show you 4 things in this region here, so pay attention. So we need to be able to find the cell values. That's one of the requirements. Those are shown in different values here, for example, in the table. Then you also need to be able to identify the column names, for example, in this case, winner ID. The table names, which tell you, for example, whether this is a country or a player or a tournament and so on. And also some logical snippets. So the logical snippets have to do with this having count greater than 3 or sorting by a certain attribute and so on. So the first paper that I'm going to talk about is called Spider. This is the first author of this paper is Tao Yu, who's a PhD student in my lab who recently finished and now is an assistant professor at the University of Hong Kong. So this Spider paper was published about 4 years ago in EMNLP, one of the top conferences in natural language processing. So as you probably know, in natural language processing, a lot of the development, a lot of the progress is done using shared tasks. Just like in computer vision, you have ImageNet and other challenges. Similarly, you have challenges in computer architecture, also on operating systems and AI. In natural language processing, typically you need to build a large data set, whether it's WordNet or some squad for question answering and so on. So Spider is the most popular data set these days, or challenge, for natural language to SQL translation. So it's fairly large, at least based on the standards of NLP. So it has 10,000 questions, 6,000 unique SQL queries. And then it is the first data set that actually has many different databases. Previous work until 2018 was primarily done on single databases. So you have training and tests within the same database. So the schema is essentially known at training time. So that makes the problem much simpler than what it in reality is. Additionally, in Spider, we have multiple tables with foreign keys that have to be joined together. You also have a fairly sophisticated SQL pattern. So you have min, max, average, but also group by having all the kinds of aggregate commands, and also nested queries. So nested queries is when you have an output that then gets fed as input to another query. And then in order to facilitate cross-domain generalization, we have split this data set into 160 training databases, and then 20 for development and 20 for testing. So what happens at the end is that during training you see certain types of domains, for example, financial transactions or electronic health records, but then during testing you see something completely different, which is one of the innovations of this data set. So this data set took a long time to develop. We estimate that it took about 1,100 person-hours to build. And it took multiple stages. So for example, you have to first find the databases, and it's not very easy to find multi-table relational databases publicly available on the internet. Then you have to clean them up, write questions, do some sanity checking, proofreading the English side, proofreading the SQL side, and so on. So Spider, when it was introduced, was fairly innovative. As you can see, all the data sets before that had very little in terms of complex queries, order by, group by, limit, and so on, whereas we have a lot more than those. And also we have a large number of databases. Now, the only thing that came just a little bit before us was WikiSQL from Salesforce, which had significantly larger number of databases, but the queries in that data set are very simple. They just have a single project and a single select, very straightforward templates that are very easy to learn. So in Spider, the data are split into 4 categories based on hardness. So you have first very simple SQL queries, just a single select project. Then you have a larger, like more complicated queries, harder and very hard queries. So one of the first systems that we built for this data set, before we even released the data sets, more like a baseline, is a system called TypeSQL. So this was published in NACO 2018, which is another of the main NLP conferences. So as you can see, in this case, we use a slot filling approach. So we use like a pair of LSTMs. I mean, this was state of the art back in 2018. And then you want to be able to predict the type of the word that is in the question. And then based on the type, to predict where it will fit into the architecture. So for example, you can predict if it's an aggregate command or column or an operator and different values. So the next thing that we tried was a system that uses syntactic structure. So in syntactic structure, we have the root of the natural language question, and then we call different modules for the different components. For example, for the select statement, we decide to use, for example, the root. The root calls a module called IEUN, and IEUN is the module that takes into account intersections, unions, and other set operations. Then you have keyword operations, you have arithmetic and logical operators, column names, and aggregate commands. So this is, by the way, I forgot to mention, this is all based on the hidden state of the neural network. So you have access to the question embeddings, you have access to the path history, the column embeddings, those are the different attributes, and then you have multiple keyword attributes for phrases and also single keyword embeddings for individual words. So Spider has become the de facto standard in evaluation of text-to-SQL systems. In fact, it was used in the workshop on interactive and executable semantic parsing at TMNLP 2020. And then we also have a new version of this evaluation coming up in the next few months, led by my former postdoc, Jonathan Kammerfeld, who's now at the University of Sydney. So Spider has led to a lot of progress in the NLP community on this task. We've had, for our leaderboard, more than 100 submissions from top research labs anywhere from Alibaba, IBM, Microsoft, Facebook, pretty much all the big players, the top universities, Carnegie Mellon, Berkeley, Stanford, and so on. And we have had, over the years, more than 50 papers, I mean, not ours, but all those different contributors, more than 50 papers published in top AI conferences such as AAAI, iClear, NeurIPS, ICD, SIGMOD, and so on. So this is the most recent version of the Spider leaderboard. As you can see, we get submissions on a very regular basis. The most recent submission that got the highest score was actually published 3 weeks ago. This is still anonymous because this paper is still under review, but we have access to the evaluation. So one note here about the main technologies used in natural language processing. As Christina mentioned yesterday, before around 2020, about 2 years ago, on many NLP tasks, including Spider, the best performance came from some basic word embeddings like word2vec. And then suddenly, you see this inflection point where all the new submissions with the highest scores come from BERT and other transformer-based models. And here in red, you can see the performance of our system. So this is the very simple baseline that I proposed at the beginning when we released this data set. And then over the years, in red are our lab submissions. Okay, so very quickly, I'm going to mention 2 other data sets that we have created since Spider. One is called SParC, which is semantic parsing in context. So in semantic parsing in context, you have the user asking harder and harder questions or more specific questions over time. They start with a simple one. For example, how many people work in the sales department? And then the next iteration, they start asking, so who makes the most money or who has been there the most years, and so on. So in each of those cases, the SQL that gets generated after every statement is based on the SQL that was generated in the previous statement. So you have to take this context into account. So I'm not going to talk much more about it, but we also have a leaderboard with a significant number of submissions. The third data set is conversational SQL. So that's when you have a user and a database interacting in a cycle. So here we have a visualization that shows you the kind of questions that you can ask. And one of the challenges in this particular data set is to do something called state tracking, dialogue state tracking. So in this case, you have to figure out what is the user really trying to accomplish. Are they trying to inform the database of something, asking a question, or following up on something existing? So leaderboard for CoSQL. Okay, now the second paper that I want to talk about was published in iClear 2021, which is last year. So iClear is a relatively new conference, but as many people here talked about, it is one of the most prestigious conferences in the field of machine learning, especially applications to computer vision and robotics and AI in general. So the paper that we presented is called Grappa. So Grappa is a system, a model for pre-training on tables. So let me give you a quick run through the system. So in order to answer questions about natural language systems, you have to be able to do some pre-training. So in pre-training, you look at a large amount of data, typically plain text, and then use this to build a model, which then can predict, for example, the next word in a sequence or a masked word in a sequence or to do classification. So the models that have been used historically over the last, let's say, 5-6 years have been primarily based on text. So, and the challenges that use those are, for example, SuperGLUE, which is a composite evaluation consisting of multiple NLP tasks such as semantic parsing and named entity recognition and so on, or SQuAD, which is the Stanford question answering dataset. Again, as you can see, those are both purely text-based evaluations. Now, what if we want to move to tables? Well, it turns out that models that have been trained on plain text, such as Wikipedia articles and books, are just not sufficient. They really don't understand tables well, even if you linearize the table. So linearization of the table means that you take it as a grid, and then you form some sort of running text from it so that at least you can use, to the extent possible, the pre-existing language models. But even that doesn't work very well. So in order to be able to use tables in NLP tasks, you have to jointly understand the questions and the table. So you have a hybrid model that takes into account both running text, unstructured text, and also structured text from the tables. And then you also have to figure out the logic, but then you cannot do this before you do the training. So the two systems that were built before us, one is called Tabert, the second one is called Tapas. So in both of those cases, they created large data sets that are trained on Wikipedia tables and the surrounding text. So here's an example. You have a table here, median age of the population in the United States. You also have some sentence that appears near this text in the document. Similarly, here you have some tennis players from number 1 ranked over the years, and then you have a sentence that describes the content of this table. But as you can probably see very easily, even from the back of the room, the text here is not necessarily a very good description of the data in the tables. It's very noisy. It omits a lot of significant information. It's also very short relative to the size of the table. So this is noisy and it's not ideal. So we need to do something better, and then we need to compare against the baselines established by those two systems, Herzig et al. And Ian et al. So one of the main ideas in NLP when you need to create a lot of data and you don't have access to manually labeled data or to some naturally occurring labeled data is to do data augmentation. So in data augmentation, for example, by this famous paper by Robin Jia, Percy Liang, 2016, they start with some original examples, and then they induce a grammar, in this case a synchronous context-free grammar. I'll explain that in a second what that means. Then you sample new examples from this grammar, and that gives you essentially unlimited access to data. It's not naturally occurring, but it's very similar. It comes from essentially the same distribution as the naturally occurring data. And then once you have those recombinant examples, you can train the model, but again, this gives you like 2 or 3 orders of magnitude more data on which you can train. So I'll skip the right-hand side. So now it turns out, unfortunately, that data augmentation alone doesn't necessarily help. So if you look at some of the recent papers by Zhang et al., Campagna et al., they did some comparisons on 2 types of data sets. So one is this SQL data sets that we created. And as you can see, without synthetic training data and with synthetic training data, the performance is essentially the same. Here you may have 1% improvement, but here you have 3% drop. So this doesn't help very much. On the right-hand side, you also have Wizard of Oz or speech dialogue data sets. And again, the performance doesn't really get better with augmented data. So what we needed to do is something different. And here's a sketch of what we did. We started first with annotated text-to-SQL examples, whatever we could put our hands on. Then we create a grammar, again, just like in the Jia and Liang paper. And just to clarify what it means to have a synchronous grammar. Synchronous grammar is where you have a single start symbol then that gets rewritten in two different parallel paths. One of the paths produces natural language, for example, questions, and the other path produces SQL statements. So at every iteration, the non-terminal gets rewritten in two different ways, and then you recursively do this until you reach the leaf nodes for both of the different modalities. So this way we create 475,000 synthetic text-to-SQL examples. On the other hand, in a different path, we start with actual tables, and then we create the tables, and we combine the grammar with the table to produce those examples. So this is what the synchronous context-free grammar looks like. So you have, for example, a table, column, value, those are the non-terminals, and then you have production rules that say root is going to produce this tuple here, alpha and beta, where alpha, the thing before the comma, is the natural language statement, and then after the comma you have the beta, which is the SQL statement. Now, a very simple engineering trick that people use in this kind of case is to anonymize, quote-unquote, the data. So anonymization means that you replace every single variable or constant with some symbol so that you can generalize. So instead of having, let's say, year 1995 and year 2015, you just have a single token that corresponds to year, because the assumption is that different values of year will behave the same way in different SQL queries. Okay, so here's what we do next. We take Roberta, which is a robust version of BERT, which is very established in the NLP community as one of the main baseline systems. We pre-train it using this synthetic data set that we just created. And then we have one loss function here called the SQL semantic prediction loss, which has to do with the set of SQL keywords that appear in the output. So for example, we have a select statement here, a none for the projection. And then you do this based on the paired statements or question here, and then the SQL statement on the right-hand side. Well, it turns out, that, as I said earlier, this is not enough. It doesn't give us any additional improvements on the performance. So what we do instead is we add an additional objective function based on masked language models, just like in most of the traditional pre-trained language models. And we do this based on questions over tables for which we don't have actually some intermediate representation. And then we combine those two losses, just add them together. So this is the masked language model, predicting which word is missing from the sequence, this one or this one, and then this is the SQL semantic prediction loss. So we just add those two together for when we evaluate the system. Okay, let's now look at the data sets that we use for evaluation. So on the left-hand side, we have two fully supervised semantic parsing tasks. So Spider, which I already mentioned, and WikiSQL, which I also briefly mentioned. In both of those cases, we have databases, we have natural language questions, and we have executable SQL code. So this is on the left-hand side. On the right-hand side, we have weakly supervised semantic parsing tasks. So this is Wikitable questions and also WikiSQL when you ignore this internal representation. So instead, you learn from something called denotation. So denotation is when you have the output of the execution, the input, but you don't have the intermediate representation that led to that particular output. So those are the four different data sets on which we evaluate our system. So there's a little bit more detail here. We can just take a look at what the questions look like and the tables and the annotations and the sizes of the different data sets. As you can see, they're fairly large, at least by NLP standards for structured data. Okay, so let me show you some of the results that we get with this combined pre-training model. So one is on Spider. So on Spider, we get actually some pretty good improvement with, this is the baseline system, RADSQL, that had SOTA state-of-the-art performance as of 2019. And then here's what it gets. So with Grappa, just using the masked language modeling, we're getting an improvement of about 1.4% over the Roberta large model. With Grappa, we're using the SQL objective function. We get an improvement of 3.9%. Then if we increase this by adding both of them, we get a slight drop in performance on dev, but we get actually 4% improvement on the test set. So here's the second data set. This is fully supervised WikiSQL. So in WikiSQL, we have the best performance here is on the test set is with Grappa. So if you compare with the state-of-the-art, we get an improvement of about 1%. But then we also did an interesting experiment with very limited data, just with 10K examples. And then we have on this kind of much smaller data set, we have a much bigger improvement in the performance. As you can see, it goes from 79.2 to 82.2. Okay, now the next data set is wiki table questions. So here we do something similar. So again, our improvement is about 8.2% in both dev and test over the baseline. But then if we look at a much smaller section of the data, we get still quite significant improvement in performance. So in this particular case, the most important number that we get improvement from 38.1 with Roberta to 42%, which is very statistically significant. And then here's the final data set. This is weekly supervised WikiSQL. So again, we get 5-6% improvement over the best system by then. So very quickly, so generalization, because the data set is the same, but we use a different training technique, we actually can observe some changes in the accuracy for generalization. So we're getting much better generalization on the two data sets because we're training on a different data set. But also pre-training, here's the most interesting result. So if you compare with the training for Tabart and Tapas, they were trained for 6 days on 100 V100 GPUs, or 3 days on 32 TPUs for Tapas. Whereas in our case, our pre-training is done on 8 16 gigabyte NVIDIA V100s, and the procedure is done in less than 10 hours. So this is pretty important as far as performance goes. Okay, so very quickly I'm going to show you some other recent numbers. So one is the table-to-text generation, NACO 2021. So in this case, we have, again, a database. Now we're trying to generate answers from the database based on user questions. So for example, the user asks, which cars get more than 100 miles per gallon? So this is like a road efficiency or fuel efficiency metric. So this is the corresponding SQL statement. Then you get the result of the SQL execution. And then you find the cars that satisfy this constraint, and you generate a sentence that says something like, the 2013 Nissan Leaf electric vehicle gets 102 miles per gallon. So here again, we spent a lot of time creating a data set based on Wikipedia tables. So here's how it works. You start with a table. For example, the largest NFL stadiums in Europe. Each of those has a representation that consists of the team name, a stadium, stadium's capacity, the year the stadium was open, so this is like a nested representation, the city of the team, and so on. So then we have a tool that automatically converts this table into an RDF tree. So RDF is a semantic web concept. It stands for Resource Description Framework, and it allows you to represent knowledge in the form of triples. So each triple consists of a verb, and then a subject and an object. So for example, if you say, I don't know, Angela Merkel is the former Chancellor of Germany, there would be a predicate called former Chancellor of Germany and a former Chancellor, and then the two arguments of that will be Angela Merkel and Germany. And the good thing about RDF is that you can nest the RDF triples and you can build an entire RDF tree. So in this case, you have team, which determines the values of stadium and city. So city depends on team, stadium depends on team, but let's say city and stadium don't depend on each other. Stadium has additional properties like capacity and the year it was open. Then in addition to the RDF representation of the table schema, we also add some metadata, which is the table context and the title of the table. And then based on this information, we create tens of thousands of questions and the corresponding triples that contain the answers. So this is a comparison of Dart with some other similar data sets, for example, Toto, Logic NLG, Wikitable NLG. So the main contribution of Dart is in the input representation, which is very versatile, again, in the form of RDF triples. Okay, so the next paper was published earlier this year. It's called FETA QA. It's a free-form table question answering. So again, the idea is that you have a table, you have a user question in free form, and you want to produce an answer to this question. So here's some of the examples. You have a table about some German submarine. Question is, how destructive is U-60? And then you have an answer that summarizes the values of the different cells that correspond to the question. And again, FETA QA is the free-form data set compared to the previous ones, which are structured either free-form but much smaller or not free-form at all. So the most recent project that we're working on is something called table summarization. So I'll just have a quick image to show you here. So you have a table, and then you want to find automatically some of the highlights of this table. For example, these are the top 10 largest movie theater circuits, and this is how many sites each of them has. So the idea here is that if you, let's say, do a web search and you want to retrieve a bunch of tables, you want you probably don't have the time to look at the tables and understand their structure, whereas this will tell you what the data is about and how to access it. Okay, now for the last couple of minutes, I'm going to mention very briefly our most current project that was just finished just very recently, a couple of weeks ago. It's a joint project between us and many other institutions, including University of Washington, University of Hong Kong, that's again where my student just went, Berkeley, Salesforce, Carnegie Mellon, Stanford, and so on. So the idea is that we want to build a system that can combine all the different structured knowledge NLP tasks into one and just create a single model that can answer all those systems together, that can combine all those systems together. So here's how it works right now. You have semantic parsing tasks, for example, which players did win the Australian Open, and then the output is something in SQL or SParC, which is another database query language. You have question answering tasks where the input is a natural language question, the answer is some free-form answer, either a table, cell, or sentence. You also have data to text generation, so you have a description of a table. You have fact verification, so based on this table, is it true that Canada obtained 3 more gold medals than Mexico? And for example, the answer is either true or false or cannot be determined. And finally, you have dialogue state tracking systems where you have exchanges over time. So instead of building separate models for each of those tasks, like semantic parsing and question answering and so on, we want to be able to build a single composite model, which is what we call unified SKG. So if you go to the unified SKG website, you can see how this works. So I will skip some of those slides here. I just want to show you the data sets that we use. There are 21 different data sets in this challenge, and they're divided into 6 categories. So here's some examples. You have semantic parsing tasks such as Spider and CoSQL. You have knowledge-based tasks. You have question answering tasks over tables, logical question answering tables. You have data to text such as Toto and Dart. You have conversational tasks, including multi-turn. You have fact verification tasks, including TabFact, which is the most popular data set for this kind of challenge. And then you also have formal language to text, which is a relatively new challenge in NLP, where you convert, let's say, from SQL or from some other structured language into informal text. Okay, so here's the performance currently of the system. Out of the 21 tasks, we're getting sort of performance on 18 of the 21 tasks. And for some of those, the 4 that are highlighted in brown here, we also use constrained decoding and re-ranking because of the specificity of those particular tasks. Okay, so I'm going to conclude in a couple of slides. So the ultimate goal of this big project is to be able to have ubiquitous natural language interactions. So if you have a question like send a list of European patients who have had COVID vaccine to Jack. So again, to Jack refers to send. So the question is, where do you get the patients from? Well, the patients come from the SQL database here. European comes from a knowledge graph, which has to be queried in SParC. And then which Jack? Well, this has to be called, like, say, an LDAP API call or something like that to find which person you're talking about, what their email address is. Okay, so that's the ultimate task. So this is the unified SKG team. Again, thanks to all of those people. Again, Tao Yu, for my former PhD student, is the leader of this particular project. And then to conclude, our project has been about closing the loop in natural language interfaces to structured data. We started with a paper in 2018 when we introduced the Spider dataset. Then over the years, we introduced all those additional tasks and challenges. And we just finished recently with the submission to archive for SKG. So I want to thank all the team members. So I mentioned Tao multiple times. So this is what he looks like. Again, he's now at the University of Hong Kong. Ray Zhang and Lin Yong, also PhD students in my lab. And then, last slide here. If you want, you can download all those different data sets and code from our website, lily.yale.edu. Thank you very much.